So if you want to take all the terms in a sequence and add them up, you'd get a thing called a series. But if we want to take all the terms in a sequence and add them up, we'd be taking presumably infinitely many things. And even if it was a finite sequence, we'd still have a chain of terms that all follow a pretty specific pattern by definition. So it may make sense to look at that pattern and say, well, why don't we just condense it down to something nicer? And that is the purpose of what we have here, which is called our summation notation, where you've probably seen this type of thing before. What we do is we say, okay, we use that big capital sigma to say, let's take the sum of things of a certain pattern, where our pattern is going to depend on our index. We usually call that index I, but we can use J or K or any letter we want for that, from our lower limit, which is often 1, but doesn't have to be 1, up to our upper limit, which usually we say is n in general, but doesn't have to be n. It's just a choice of notation, where we're taking sum of things of terms ai, which means that we're just adding up things that follow that pattern, ai. And this is clunky notation, certainly the first time you see it. A lot of students really don't like summation notation until they get a lot of experience with it. So instead of sticking around here just looking at this Greek letter and all the notation around it, we're going to get our hands dirty with a couple of examples here to finish the section. So for our first example, we want to express the sum 2 squared plus 3 squared plus 4 squared plus 5 squared using summation notation. So for this, what we want to recognize here essentially is the types of patterns that occur in that addition, so we can condense it down into that, not nicer, this is a strong word, into that more, let's say, concise notation there. Where what we can see is, if we look at this carefully, we are starting at something like n equals 2 and going up to some value 5. So we're going from 2 to 5, and I'll just call them squares. So if you want to think about what this is going to give us in terms of that kind of pattern, 2 squared plus 3 squared plus 4 squared plus 5 squared. Well, if we want to pull that in, we have our sigma, where we're starting at 2, so I'll say I equals 2. Like I said, you don't just start at 1, but we often do. You could make it 1 and then readjust. It's called reindexing. We're not going to worry about reindexing too much in this class. Anyway, we're going to start at I equals 2, and we're saying we're going from 2 up to 5. So we're going from 2 to 5, and we're following the pattern an of squares, where we're using the index I, so we're just taking terms I squared. And that's it. We're just saying that instead of looking at this sum of things, we're going to use this guy as a bit of a language shortcut to just pull it together a bit. It's not necessarily nicer, but it is a little bit cleaner, especially if we're going to talk about larger summations than just 4 things. The summation notation with a case of just 4, it's not the most useful really, but to understand the language, we're starting out small. Even dwarf starts small after all. But we're going to keep building on this with a couple more examples. So for our second example, we want to expand and evaluate the sum from I equals 1 to 3 of 5. It's a bit funky. But what we should be careful of here is to note that this doesn't just say take 5 and that's it. This says we are looking at a pattern of 5s added 3 times. That is, this guy says we're going to start at I equals 1 and go to 3. Where at each of those, we get 5. So at I equals 1, we get 5. Plus, at I equals 2, we get 5. Plus, at I equals 3, we get 5 again. So we get 15. And that's it. And that's not a very notational example now, is it? So we'll finish this section with one that has more than one number in there. It's more interesting if there's more than one number. So for our last example, we want to expand and evaluate the sum from j equals 3 to 6 of 1 minus 2 raised to the power j. Again, like I said, you don't need to use I for your indexing letter. It's the most traditional one, but sometimes you want j or k. Here we're using j. But what this says is we want to take the sum of things where we're going to be starting our things at 3 and running our things up to 6, where our things follow the pattern 1 minus 2 raised to j. So for our first term, we're at j equals 3, and that means we're going to take 1 minus 2 cubed. And then our second one, we're going to go up from 3 to 4. We're going to take 1 minus 2 to the 4th. Then for our third, we're going to have a 1 minus 2 to the 5th, plus a 1 minus 2 to the 6th. And actually, that's it. Try to get ahead of myself to say that there's more than 4 things, but really it's just 4 here, where 2 cubed is 8, 2 to the 4th is 16, 2 to the 5th is 32, and 2 to the 6th is 64. So we will have negative 7, a negative 15, a negative 31, and a negative 63 for a total of negative 116 for that sum. Sums can be negative. If we're adding up negative things, we'll get a negative number. And this is essentially what we've got here to just introduce ourselves to what summations look like and what generally sequences are. In our next section, we're going to look at a specific pattern that we get with our sequences, where we're talking about ones that occur from taking repeated additions with things called arithmetic sequences, but that's a topic for 10.2, which we're going to be seeing next.